So here we're going to talk about the modulus function. I'm going to try and keep it reasonably short and rolling on from here. So the modulus function is this. It's written with absolute value signs. So you've got the modulus of x, two straight lines, and basically it makes any negative value positive. That's essentially what the modulus function does. Technically, mathematically, it's written like that. So it's written as a piecewise function, which we haven't really fully covered in methods, but we are going to cover quite soon. But hopefully you can understand what that piecewise function means. It says that if x is greater than or equal to 0, then the modulus of x equals x. If x is less than 0, then the modulus of x equals negative x, and we all know that negative of a negative number makes it positive. So, but you don't have to worry about too much about that notation. You just have to know a modulus function makes any negative value positive. That's it. You can, and that's brought up in the textbook. It's used. I don't really use it that often. It is another way. It's a way that you can solve modulus equations. In my humble opinion, it makes things a little bit more complex. So you can either split it up and say when it's positive, it stays the same. When it's negative, it becomes negative of itself. Or you can square both sides and solve that way, but then you end up with quadratics. Sometimes you end up with square roots or quartics. It gets a bit out of hand. But you'll see examples of that in the textbook, so that's a good point. So the modulus of 6 is 6. And the modulus of negative 10 is 10. Easy. Good. That's question 1 of the textbook exercise. On with that. Determine the values of x such that 2x minus 5 is less than negative 1, or 3x plus 8 is less than 4 with the modulus signs around them. Any thoughts? Let's start by playing a bit of a game with A or B, or 1 or 2. Tell me if you can think of an x value that makes that inequality true in either case. For the first one or the second one? For the first one or the second one? First one. 2 times negative 3 is negative 6, minus 5 is negative 11. The modulus of negative 11 is 11. Is 11 less than negative 1? No. Any other takers? No, its modulus is around the whole thing. If the modulus was around the x, then 2 times 3, that would work, you're right. Well, no, actually it wouldn't, but it would be equal to. So?
Make negative 1 an anti-modulus.
What's the inverse of a modulus? Can you just move it to the other side?
You would have to probably write it as 2 separate equations. So, yeah. But I think I need you to think a little bit more about the definition for number 1.
Yeah, how can you get a modulus?
So, is there any answers for number 1?
Oh, it's a trick question.
The modulus is always positive. But I want that in your head. I want you to be thinking, you're in an exam, you get a modulus question, and we wouldn't give you a trick question like this in the exam, but you get a modulus question and you look at it and you go, oh, hold on a second, it was at the time Mr. Manson was really annoying in class and set up a trick question first, and hopefully you remember it. So the first one, the modulus of anything is always positive, so it can never be less than negative 1. So that one doesn't work. Let me write down here, no solution. I can't do that now because you know. So that's the kind of thing you come up quietly and just say, hey, can you treat the rest of the class? Yeah. Anyway. Okay, part 2. Negative 1. X equals negative 1 will give us 3 times negative 1 is 3. 3 times negative 1 is negative 3.
Negative 2.
Okay, negative 2 works. Any other takers? Negative 3 gives us negative 9 plus 8 is negative 1. Modulus negative 1 is 1. So that works. Yep. Negative 4. Okay, negative 4 doesn't work. Xander, I like mathematical discussions, but let's just calm it down. Okay, on our number line, remember I've noted here ladies and gents, so if I could just get people listening again. I've noted here that we can represent modulus inequality on a number line, just like we can just with general inequalities. And on this number line, if I have 0, so I won't have 0 there, if I have 0 up here, we just noted that -2 exists in the band, -3 exists in the band. -4 doesn't, but only just, because -4 gives us 4 is less than 4. So -4 is actually an important value on a number line. It doesn't exist, we put a circle around it. It's the lowest number that doesn't exist. -2 doesn't work. And in fact, if we want to get the end point is for what value does 3x plus 8 equal 4 with the smallest possible negative number? And so that will be 3 times what will give us -4, and that will be -1 1/3 or -4/3. So the lowest value is about here at -4/3, and that's also not included. And on a number line, these are all our solutions. This question will get a bit easier later on. I'm going to show you how to do it more algebraically, but this was a thought experiment. This was for you to just try and think through the problem and what makes it work. And for most of you, caught on to the fact that you needed the 3x plus 8 to be less than 4 or greater than -4, and then it works. And you've just dealt with that. So let's talk about graphing the modulus function. Y equals the absolute value of x. I've drawn it here for you. So remember, the modulus function makes everything positive. So if you just have the modulus around the entire function, it just gets everything that's in a negative and flips it up. That's all it does. It's really easy. But we can still apply transformations to it like we do with other functions. So we could do y equals the modulus of x minus 2, and that would shift the whole modulus function down. If we had a minus 2 in the end, it wasn't inside the modulus, so it can still get negative values in a modulus function. So I've got another example here. Let's sketch a couple. Sketch x squared minus 4 modulus, and then sketch the modulus of x squared minus 3, the modulus of x. And then sketch the modulus of 2 cos x minus 1, and then sketch the modulus of 2 to the power of the modulus of x plus 1. I can. So I'd like you to set up some axes in your book. I'd really like everybody to take part in this activity. Okay, sketching the modulus function. I'm going to set up an axis. I'm going to do A and C first. There's something special about B and D that I want to try and get you to work out. But let's start with doing A and C. So in black, I'm going to draw the actual function. X squared minus 4 is just a parabola. It's been shifted down 4 places. So it goes down to minus 4 is where the turning point is. The parabola looks like this, approximately. And the modulus function, all the positive values stay the same, but now it flips up. So it does a bit of this, and then it stays the same. So, I mean, I want you to sketch this on desktop and play with it, but you might not recognise that this is the reason why. So you need to know the reason why. In black is the original function. When you take the modulus of that function, everything that's negative just gets flipped. It's like it's bouncing off the ground. So that's the first bit. The second one I'm going to do on the same set of axes, in red, I'll draw the standard function for 2 cos x minus 1. 2 cos x minus 1, if you go back to term 2, it has a midline of 1, it has an amplitude of 2. So it has a midline here at the red dotted line, has an amplitude of 2, so it goes up to there and down to here. And of course, cos starts at a peak, and it has a period of 2 pi. So my scale's going to be a bit out because this value here is 2. That's where the x-axis goes. So it's going to look like this. It's going to go like that. And the same thing happens again though. This time, in purple, the negative values reflect up. So here's our critical points, there and there. And the negative values flip up from -3 up to 3. So I draw a little dotted line to there. And at this point, it flips up. So now it does this. And then it flips again. Is that what it looks like, Harvey? So that's what that will look like. If you just do the modulus of cos, it looks a bit more normal. But because we translated it down, it creates that we've got a more in the negative area, so it creates a small hump, big hump effect. So, and think about that, what happens. It would be a lot easier if we translated it down enough so that none of it was in the positive. That would just reflect the whole thing over. And it would still look like a cos function just flipped over. But it's only when it does cross over the x-axis you get some weirdness going on. But if you draw, and if you can sketch the original function, drawing the absolute value of the modulus function is trivial. You just have to then flip all the negative bits up. So I encourage you, if you ever have to sketch one of these in the exam or anything like that, just draw the original function, flip it up. That's the easiest way to do it. Any questions? Those x-intercepts are really important. They're your critical points. Now, the difference is that here, that is, and that is, sorry, Xander, just give me a second. A and B and C are absolute value of functions. So the absolute value, everything happens inside the modulus. With B and D, the modulus is happening first, so all the x values, all the negative values are becoming positive, and then we're doing the function. That's the difference. So this creates a reflection the other way. And I'm going to go through and draw these in a second. Xander, what was your question, sorry? Or comment?
So they do intercept.
Yes, because zero, the modulus of 0 is 0. So when it's equal to 0, you get 0 still. So it touches, bounces off. Okay, so I'm going to sketch this other function. So in B, let's take B for example to start with. In B, the absolute value of x is either x if x is greater than 0, or the absolute value of x is negative x if x is less than 0. So what I'm going to do is I'm going to split this set of axes into two parts. I'm going to deal with the positive section first and then the negative section. Let's start with the positive section. The first function is x squared minus 3x. So I'll call this 1 and I'll call this 2. In 1, we're sketching y equals x squared minus 3x, which is x times x minus 3. So it has x-intercepts of 0 and 3. So I'll plot that on there. There's 0, there's 3. And it's a positive quadratic, so it does what we expect. It looks like this. There we go. That's in the positive section. In the negative section, part 2, y is equal to, this time we're saying, instead of a negative value, we get this. We get negative x squared minus 3 times negative x. So we know that x is negative, so we have to negate that because that's what the modulus will do. It will negate that. So we get x squared plus 3x. And that gives us a factorization of x times x plus 3. And so in the negative section, we get an x-intercept of 0, and we get an x-intercept of negative 3. And so our function will look like this. And I hope you can see that this is now a reflection over the y-axis. And it makes sense as a reflection over the y-axis because on this side, x is positive, and on this side, all the negative x actually take on the result when those x values are positive. So when x is negative 1, it's actually treating it like 1, so we get the result when x is 1 at that negative 1 point. When x is negative 2, same thing. So if you get one where it's the modulus of x inside the function, then now we're talking about sketching the positive side and then reflecting that to the negative side. And so the other one is, which I'll do in blue, the other one, which is D, is sketch y equals 2 to the power of modulus of x plus 1. And then for the modulus of x equals x, if x is greater than or equal to 0. And the modulus of x equals negative x, if x less than 0. And so sketching this is the same thing again. We start by sketching 2 to the power of x. It starts at 0, 1, and it's an exponential, so it goes like that. And then we just reflect that on the other side, because when we do 2 to the power of x, but x is negative 3, we get 2 to the power of 3 again, because the modulus of negative 3 is 3. So we get that reflection, except in this case, and I've just realised I've forgotten about that plus 1, so I'm just going to rub that out. In this case, it goes through 2, 0, 2, because 2 to the power of 0 is 1, 1 plus 1 is 2, and so it's an exponential function that goes like that, and then it goes like that. You've got to be careful here, and I've not done a very good job of it, but an exponential, it's not going to be a smooth curve here. And this is something we're going to cover in math methods quite soon. We'll talk a lot about this early next term. But this should look a little bit, not discontinuous in terms of the point, like it's continuous here, it meets at 0, 2, but the gradient will be discontinuous. So it's going to have a little bit of sharpness at that point because it's a reflection. It's not going to be smooth like a parabola is. So you have to be a little bit careful here that you don't make it look too much like a parabola. But unfortunately, the way we set this question up, it's probably going to be pretty smooth. Any questions on that? That is it for sketching. I do have a second section, solving modulus equations, that I need to go through with that example, but I think I might split this lesson in half. So I might give you some time to do that. So I'll stop this now.